Welcome everyone. Today is a tutorial for quantum information and chemistry, which is a workshop run by the Initiative for Theoretical Sciences at the Graduate Center. And it'll be this Friday, December 3rd, from 11 a.m. to 1 p.m. Eastern time. And we're going to hear 4 speakers talk about quantum information and quantum computation research. So the purpose of this tutorial today is to kind of give introductory or beginner level understanding of some of the concepts, which they'll explain more in depth in their talks this Friday. As for the style of this talk, this is meant to be more of like an informal talk. So if you have any questions at any point, just please raise your hand and interrupt me right away. And we can have discussions about whatever questions you might have. All right. So with that, I want to motivate this talk by first saying that there's a lot of interest in the field of quantum computation and quantum information in general. I've listed some of like the really big name companies here, which have quantum computing teams and have invested a lot of money into building quantum computers and doing fundamental research. And there's a large number of established companies and startups with a lot of money poured into them because quantum computers have a lot of potential, and I hope to be able to show that to you today. I've listed a website here quantumcomputingreport.com/players, which allows you to see a lot of breaking news and also a list of startups, big companies, and also academia at this link, really all related to quantum computing. So question is, why are we interested in quantum computers? And basically, you use quantum computers is a different kind of physics, and because of that, they have the potential to solve certain kinds of problems much faster than classical computers. So already it's been shown like that if you use Shor's algorithm for factoring integers, that you can factor integers much faster, that scales much faster on a quantum computer than a classical computer. And the same thing for a certain kind of search algorithm. And these problems have kind of like wide range of applications. So when I talk about factoring integers, the reason why factoring integers becomes important is because factoring integers is a part of RSA encryption, which is a lot of how it's basically how our messages are sent securely. So and there's a lot of talk about how quantum computers might be able to might break certain kinds of encryptions that we currently use. And what makes quantum computers unique is that the underlying basis for how computers work is much closer to quantum physics than classical. In classical physics, you have your equation of motion given by F equals ma, and in general, it's deterministic. So meaning that you can know the position at a certain time, and you can know the momentum at a certain time. And if you could solve the equations of motions, you can get the position of momentum exactly for not only the initial time, but for all future times. But the quantum case is different. For the quantum case, the equation of motion is the Schrodinger equation, and it has what's called the wave function in it. And the wave function is inherently different because the wave function gives you probabilities of finding your particle. So you don't know exactly where it is, but you have the probability distribution for where it could be. And so there's an inherent uncertainty until you do the measurement. And in addition, you can't know the position and momentum precisely at the same time. That would violate the Heisenberg uncertainty principle, which I've written here. As a specific example of classical physics, I've shown the harmonic oscillator. If you have the harmonic oscillator is basically a problem where you have, say, a ball on a string, and so the Hamiltonian is given as follows, and basically the point is you can see the solution right here, which gives the equation of motions for all future times. You know x, you know position, you know momentum, and you know them for all future times. On the other hand, for the quantum harmonic oscillator, which is the exact same potential energy, the solutions look different. The solutions are for the wave function, which are on the left. And with the wave function, the basic tenet is you have to square the wave function to get probabilities. So on the right is the probability distribution of finding the particle at certain places. So how do we understand these probabilities? Well, the Copenhagen interpretation says that the idea of measurement is very important. So before you measure a quantum state, there are many different possibilities. But after you do the measurement, you sample from the probability distribution, and you should only get one result. And so that's what they mean by the wave function collapses to the measurement. From the Schrodinger equation, you can predict only the probability of the result. So you can only get the probability distribution. And so we're going to see all this play out in a quantum computer, where the things that we measure are called qubits. All right. Any questions so far on what I've discussed? All right. So I'm going to be talking now about the difference between the classical bit versus the quantum bit, which is called a qubit. A classical bit is fully deterministic, 0 or 1. And meanwhile, qubits can be a superposition of 0 and 1. So I've written an example here. They could be thought of simultaneously to be 0 and 1. And so it implies greater computational power because it has states which classical bits can't describe. The qubits are the qubits and the operations done on them are described through linear algebra. And so you have two states, the 0 state and the 1 state. And as you can see from the top, they could be represented in vector notations as 1, 0, 0, 1 respectively. And then onto each bit, you can apply certain operations. The operations will be square matrices, and they'll change the bits. So shown in the box is an example of the NOT gate or the X gate. Similar to the NOT gate in classical computers, what this square matrix does is when you multiply the gate X onto 0 from the left, you'll find that it flips the vector, so it becomes 0, 1. So it'll become the vector 1. And likewise, when you apply X to the when you apply the NOT gate to the state 1, that flips it into state 0. And what's shown here in this rectangle is the square box of 0, 1, 1, 0. That's meant to show the that's meant to represent the gate of X. So in addition, the qubits can take on a whole range of values, which are represented by the block sphere. So here we have the block sphere is meant to be a pictorial representation of the states that the function could take. When if the vector points straight up as 0, that means that the qubit has a 100% chance of being in state 0. And if it points straight down, then it has a 100% chance of being at state 1. And that makes it similar to the classical case. But as you could see, the vector could also point into any other direction on the sphere. And in that case, you would have a superposition, and you can have, when you do a measurement, then you can get values of 0 and 1. Right. Also similar to classical computation, what I previously defined was a gate acting on 1 qubit. You can also define gates acting on 2 qubits. In this case, you'll see that the vectors corresponding to the 2 qubits has a length of 4. And you'll see that the square gate corresponding to 2 qubits has to have dimension 4. The C0 gate, is when applied to the qubit state 0, 0, which implies that both qubits are in state 0. What the C0 gate is if the first qubit is 0, then you do nothing, and then you do nothing. But if the first qubit is a 1, then you flip the sign of the second qubit. So in the first case, when you apply C0 to 0, 0, since the first qubit is 0, nothing changes. Everything is the same. In the second case, where C0 is applied to the state 1, 0, first qubit is a 1. Because of that, you are forced to flip the second qubit, so you get 1, 1 as your output. And likewise for the right side, when you do C0 on qubits 1, 1, since the first qubit is a 1, you flip the second one, you get 1, 0. And basically this C0, because it has an interaction between 2 qubits, can be used to produce entangled states, where the value of 1 qubit depends on strictly on the value of another. Any questions about the gates which I've shown, or the vector representation of qubits? All right. So one thing I should emphasize that makes qubits more advantageous than classical bits is I've shown examples of a 1 qubit gate and 2 qubit gate. And now I'm showing you an example of a 3 qubit gate. But you could see that in general that the sizes of the matrices are exploding or getting larger much quicker. So the dimensionality for n qubits is 2 to the n, whereas for n classical bits, it's only 2 times n. And it's thought that this higher dimensionality allows it to sample more regions of space. And so I want to talk in general about this idea of quantum supremacy, which is the idea that quantum computers could do certain calculations faster than classical computers. What the things that make qubits better than C-bits are the high information content, meaning that you can have both 0 and 1 at the same time in 1 qubit. And also there are, and also in a sense, because you could have 0 and 1 at all kinds of different proportions, there'll be, you can encode infinite digits inside a single qubit. It also has high information content because when you have n qubits together, the dimension is very high, it's 2 to the n. You also have the bonus that since the wave function is probabilistic, it could be thought to sample the whole space, so it could be thought to be massively parallel. And then it might be able to solve more complex problems. So it's thought that it's possible that quantum computers could solve more problems in polynomial time than classical computers. Even though that's not, that's not yet proven, it's thought to be so. Okay, and but the problem is that so you can demonstrate quantum supremacy when a quantum computer is strictly faster than a classical computer at a certain problem. But despite all the plus sides I've talked about the potential in quantum computing, as of right now, I don't think there's any useful problem for which quantum supremacy has been demonstrated. And the problem with quantum computers is that there's real difficulties related to the qubits. Basically, the problem is that the system has to be protected from the outside environment. If the system interacts with the outside environment, then you're introducing errors into your computation. A qubit could be flipped from a 0 to 1 in ways that are unintended, or the signs relative, in a superposition, the relative phases could change over time. And so in that sense, the system has to be somewhat closed, but then the quantum computer also has to be, you also have to apply the logic gates to the system. So they have to undergo certain operations, which such as excitations. And so in that sense, they have to be somewhat open. So in general, like what is the hardware of a quantum computer? It's basically, it's a qubit, which is a two-level system separated by an energy difference. And it could be basically anything which satisfies those properties. So it could be related to it could be related to the atom's ground state and excited state. It could be photons. It could be anyway. It could be any of these things as long as it satisfies this criteria. And so here's an example of a qubit, some actual quantum computing hardware built by D-Wave systems. They have the qubit in states of 0, 1 based on whether the magnet is up or down, I believe. Sorry, not the magnet, but the the electric field was up or down. There are many qubits, and they're because of the construction of this because of the construction of the qubit, it has to be shielded from electromagnetic radiation. So and it has to be shielded from electromagnetic radiation so that there aren't spontaneous flippings. And then it also has to be at an extremely cold temperature. So their system is at 0.015 kelvins, which means and it's required to be at that. It's required to be at an extremely low temperature because temperature means that there's enough energy in the surrounding molecules such that they can spontaneously excite the system from 0 to 1. The higher the temperature is, the more the spontaneous excitations can happen, which can ruin a calculation. And yeah, that's why the 15 millikelvin temperature is required, so that the time the spontaneous excitation from the ground state, just due to the temperature, is extremely low. In this case, 10 to the -6. So I explained how there hasn't been any real useful cases of quantum supremacy demonstrated yet. This is a paper from 2019 which first claimed quantum supremacy for a certain problem, published by Google. And this is a drawing of a circuit which is meant to show like the operations done on each gate. And what you'll notice here is that there are a lot of one gate operations, but then there's also two gate operations represented by the connections between the lines, between the rows. And the focus of this paper was to simulate this quantum circuit. And the circuit is basically chosen so that it produces really highly entangled states and over a large number of qubits. So it's basically a problem constructed in such a way as to be really, really difficult for classical computers and not too difficult for quantum computers. And there's no well-known useful application for this problem besides, in the paper, they say that it could be useful to generate random numbers, but yeah, there's not. So yeah, this is an example of quantum supremacy that's been probably been demonstrated, but not for a useful problem. And I wrote a bit about why it's so difficult for classical computers. It's in the problem they had to simulate 53 qubits, and so that means that the quantum state can't be easily stored in memory for a classical computer. Because remember, we're talking about 2 to the n power just to store the vector, so that'd be 2 to the 53rd power. And so that's what makes it scale exponentially the larger the circuit is. And finally, I wanted to say that if you're wondering where we are in terms of, for example, factoring integers using Shor's algorithm as a real world example, the quantum computers there are currently factoring like using Shor's algorithm. I think they might have factored like 35 into its primes, 5 times 7, with some error, or they factored 21 successfully, I know. So in a sense, a lot of this is in a very early stage, just because of the current quantum computers haven't found a way to overcome the noise issue in a reliable way. And so with that, I think that gives you enough of a background to be able to understand the terms, some of the terms discussed on Friday's talks. The talks span a large range of areas, some of them talking about actual physical systems to simulate quantum computers. Some of them talking about what could be done with the current quantum computers, which are noisy and have to have error correction, and other current applications of quantum computing. I'll leave you with the resources I used for this talk. A very good introduction to these to the field of quantum computation, and quantum information is this book by Nielsen and Trang. And I've also included the homepage of my professor who taught a quantum computing course at the Graduate Center. There he has a syllabus for the course that he taught, and he also has some of the lecture notes. So I'll leave this page for you guys to look at the references if you're curious about looking into it, more of this further in preparation for the talk on Friday. And I'll ask you guys if you guys have any questions or comments about quantum computing. If that's the case, oh, sorry, I see a chat. Thank you. Oh, appreciate it. Thanks everyone for listening to the talk, and hope to see you guys on Friday for the talks by the researchers in these fields. Right. Have a good one, everyone.